Yeah, so as you said, I'm Phil Relton. I am a third year PhD student at the University of Cardiff, and I work mostly on the data analysis side of compact binary coalescences, so the mergers of binary black holes and binary neutron stars. And I've been focusing on a case that is not particularly relevant in LIGO, but as we move to third generation detectors or even late stage second generation, we should start to see so many events that these transients overlap each other in time, which is a big problem. So a lot of the basics on gravitational wave detection and interferometry have been covered expertly. So thank you very much to those previous talks for saving me that effort. And I'll show you a little plot of an in-spiral of a gravitational wave here. So this is a binary black hole as seen in LIGO between about 20 hertz and its merger at I don't know what the merger frequency was, but this is a 30 plus 30 mass black hole, binary black hole merger. And this is visible for a couple of seconds in the data. And you can also have binary neutron star mergers, which have lower masses, and so they're visible for on order of 100 seconds in the data. And these signals, we've seen about 90. We saw them at a rate of about one per week and a half, I think, in the last observing run. But that's because our detectors, while they're excellent, are not great at viewing large volumes of the sky. So this is what a signal like this would appear like in the data. But if we were to have two signals, you might end up with the detector seeing something like this, which doesn't match anything like our template banks at all. It doesn't match GR because why would it? And so data analysis techniques will start to break down. Just to mention, there are other types of signals, burst type signals, but these are as yet unobserved and so are very difficult to view. I'm trying to get rid of this thing at the bottom, but I apologize. So we haven't seen burst signals, so I'm not going to consider them. So the process of analyzing gravitational wave data has been covered briefly by Connor, but essentially there are two main types of pipeline. Modeled, which is like PyCBC, as he mentioned, where you build a bank of templates, you match those templates to the data, and you see which templates have loud SNRs. Or you can have weakly modeled searches. So these search for coincident times in the data where there is excess power. And then builds up and reconstructs the waveform from that excess power as the time frequency maps show in between those detectors. So then you receive a section of data that has a signal in it, and you want to build up a set of parameters that describe that binary. And so for that, we use parameter estimation. And in particular, stochastic sampling is quite frequently used. And so you select a set of parameters, you generate basically a more precise template, you match that to the data, and you see what happens. And this is a little GIF of an example of that on the right, where I took some of the samples from a analysis set I did in zero noise, where the blue line is the injected signal and the red is what the parameter estimation software selects. And then this is just a difference plot of the two. So we wanted to see what this would look like in the case of overlapping gravitational waves. So we injected two signals into the data. We focused on binary black holes for speed. So we inject a signal at a mass of 28. The chirp mass, it's a parameter which describes binaries well. You just sort of go with it. It's a gravitational wave thing. And then this distribution here, this histogram shows the recovered parameters for that injected black hole system. And here's an equivalent for another signal at chirp mass of 24. And then we have these where we injected them at relative times. So this is where signal B merges 0.1 seconds before signal A, and at a slightly lower SNR. And you can see when they are close in merger time, you end up with sets of parameters that differ drastically from the injected signal. So that's quite a big problem. So we ran this on a set with different masses of the secondary signal, different signal to noise ratios of the secondary signal, where we kept signal A constant at SNR of 30, different phases and different merger times. And the key dependencies, well, all depended on these. Obviously, other parameters will affect it, but the main thing is the relative merger time and the signal to noise ratio. And so other people did some studies published around the same time as my study in this, which backs that up quite nicely, which was very satisfying. And we also looked at when this might happen. So I'm not going to go into the details of this calculation or most of this table, but essentially we are about here. We've completed this observing run, and we saw approximately that number of events. This observing run is about to start in December, hopefully. And we don't expect to see this at all until the late 2020s with LIGO Voyager. But the main takeaway from this parameter estimation study we did was that we don't know whether a stretch of data has one signal or two. And also, I guess the second takeaway is, even if we did, we have no method of subtracting the signals from the data, and we can't rely on any parameter estimation we do on this stretch of data. And this signal is just a waste of time. Well, for us anyway. So we wanted to see, well, can we find a way in our search pipelines of spotting when this is the case? Do we even catch these signals when they happen? And yeah, is there a way of spotting them? So this is a spectrogram or a time frequency map of two signals we injected, where we have signal A merging at about 150.6 seconds in this plot, and signal B merging just before. And then you have this region here where they are overlapping in time. This is a sort of standard chirp-like behavior of a binary black hole, this spike. So we did some analysis with search pipelines. We're running three sort of sets of injections. So we have data where we have two binary black holes overlapping, or short signals, two binary neutron stars, or long signals, and then the case where we have a binary neutron star with a binary black hole merging in the in spiral of that neutron star. So you have this non-Gaussianity or in the data, or almost sine-like behavior of this long in spiral of the neutron star, and then the chirping of the binary black hole somewhere in that. And then we want to see which of these signals we can distinguish. Can we distinguish the first signal in the pairing, the second signal, and can we catch both signals at once? So we run three injection sets for each of the three types of run, where we see whether we can detect each signal in the pairing independently, and then whether we catch the pairing at all. And we wanted to run this with matched filter pipelines like PyCBC, and with a burst-like or a unmodeled or weakly modeled pipeline like CWB, which is coherent wave burst, because we felt that a unmodeled search is more likely to catch these cases because a modeled search won't, because you can't model the overlap. Is that my 2-minute warning?
2-minute warning.
Brilliant. So this is ongoing, as shown by this big red stamp. I have results that were fairly promising, but I'm rerunning them because there was a slight glitch, unfortunately. But one of the key things we found is that coherent wave burst as a search could pose a solution to this problem entirely. So what it does is it finds coincident times between detectors where there is excess power in the data outside the standard Gaussian noise-like behavior. And then it tracks down sky locations such that the travel time between the detectors matches the power in between those detectors. And this plot on the right is just the same data as this spectrogram here. But what it's able to do is it's able to analyze where that coherent power is. And you can see in this likelihood plot of where it thinks there is a signal, it's managed to identify two chirps, unfortunately, but clearly one chirp, and one chirp slightly less. And then in the null or the residual, where it subtracted this coherent power, it mostly finds just signal B. And so in this case where we have two very loud signals, it might be possible for coherent wave burst to spot one of these sky locations, subtract the data, give us a clean stretch of data for parameter estimation by reconstructing one or both of these waveforms. And it's possible we could run this iteratively on these stretches of data to narrow down the coherent power even more precisely. So yeah, that's all I had to say. So if you have any questions, please let me know, and I'll try and get rid of that. No. Yeah, thank you very much.
Thank you very much, Philip. Again, perfect timing. People have planned their talks very, very well. Oh, we have a question. I thought there wasn't any. From Marion. Why isn't using the spectrogram the default if there's less overlap in 2D than in the time series data? Just more of a pain to analyze?
Yes and no. So the spectrograms I showed were for very loud signals. These were SNR of about 60 each, I think. And when you go to lower SNR, some of these chirps are not particularly obvious. So the standard technique is to just take your time series data of strain and do your analysis. There are proposed methods of machine learning searches that use the spectrograms, because obviously they're an image, and that's what machine learning is often done in. It's the typical form. So yes, the idea is that you could use spectrograms, but it's less done at the moment, and we wanted to use current techniques.
And I had a question on slide 5, just out of interest. As you raised the SNR of your competing signal, it seemed like the chirp mass estimate sort of smoothly transitioned. That, like at SNR 15, it's weird it kind of guessed in between rather than choosing one or the other. Do you understand what's going on there?
That is because I picked the nicest plot. There are about 100 of these, and they go drastically. This one shows the trend really nicely. And there are more runs where I increased signal B's SNR, so it's louder than signal A, and it sort of goes back up towards signal B, because you end up with ones that look like this all over the place.
Right.
It's just this one looked nicest, which I guess is not entirely helpful.
No, fair enough.